Hello everyone, welcome all of you to this video lecture series. Myself Dr. Ranjana. This is the second lecture of fourth module, that is use of free energy in chemical equilibria. In last lecture we have discussed and revised some common terms of thermodynamics, and today we will start with thermodynamic function, that is energy, entropy and free energy. In energy terms, we will discuss internal energy, enthalpy and heat capacity, right? And let's start with internal energy. Internal energy. What is this? Internal energy is the sum of all type of energy present in atom or molecule present in any system, right? It is the energy possessed by a system due to vibrational, translational and rotational motion of the molecule. It means it is the total sum of kinetic energy, potential energy, rotational energy, vibrational energy and all that. Any system is made up of atom and molecule, and it is the amount of energy present in atom or molecule present in any system, right? It is denoted by E or U. Okay. This internal energy is a state function. It means it depends upon state of the system, not on the path of the system, right? Path of the change, right? That is, del E will be is equal to E final minus E initial. What is E final? It is the internal energy of final state, and E initial is the internal energy of initial state. These are the some characteristics of internal energy. This internal energy is extensive property. It means it depends upon amount of substance, amount of matter present in the system. If you change the amount of matter in any system, internal energy will be changed because it is the energy of atom or molecule. If number of molecule or atom will be increase or decrease, then internal energy will increase or decrease, right? Then next point is this absolute value of E for any system, that is absolute value of internal energy can't be determined. You can't estimate the amount of internal energy present in any system, that is E can't be determined. But change in internal energy can be estimated, right? When any system changes its state, okay, when any system goes from state 1 to state 2, then the internal energy will be changed, and this change in internal energy, that is del E, can be found. But you can't determine absolute value of E of state 1 or absolute value of state 2 for internal energy, right? Then SI unit of internal energy is joule, as it is a form of energy. Okay. For exothermic reaction, this del E will be negative, and for endothermic reaction, this del E will be positive. It means in case of exothermic reaction, the internal energy of product will be less than internal energy of reactant, and in case of endothermal reaction, internal energy of product will be more than internal energy of reactant, that is del E will be is equal to E product minus E reactant. Then according to first law, this del E will be is equal to Q minus W. First law of thermodynamics is that change in internal energy will be is equal to amount of heat absorbed by the system minus work done. Right? It is the expression for first law. Before discussing this enthalpy, we'll discuss this first law of thermodynamics because it has the concept of change in internal energy. That is, change in internal energy can be determined. What is first law? It is the law of conservation of energy. Energy can neither be created nor be destroyed. Okay? Whenever a particular type of energy disappears, equivalent amount of another type of energy must be appear. The total energy of a system and surroundings remains constant. It is impossible to construct a machine that can produce work without spending energy on it. Right? These are some statements of first law. Then come to mathematical expression for first law. Right? Consider a system having internal energy E1 absorb Q amount of energy, and then this system changes its state and internal energy of a system changes from E1 to E2, and then W is the work done by the system. Then you can find this change in internal energy, that is E2 minus EV will be is equal to this amount of heat absorbed by the system minus W2. It means this amount of heat absorbed by the system is utilized in increasing the internal energy and for the work done by the system, and this is the expression for first law, that is del E is equal to Q minus W. Okay, if this work done is a pressure volume work done, then this expression can be written as del E will be is equal to Q minus P del V. Right? These are the expressions for first law. Then for special cases, special form of the first law. For first case, for isothermal expansion, when the expansion of gaseous system takes place isothermally, then del T will be 0 in the process. Then as change in temperature is 0, del E will be 0 in that case. Then amount of heat absorbed by the system will be is equal to work done by the system. Right? Then second case, for isochoric process. For isochoric process, del V will be 0 and P del V will be is equal to 0. That is, pressure volume work done will be 0 in the case of isochoric process, and in that case this del E, that is change in internal energy of a system, will be is equal to amount of heat absorbed by the system. This QV is the amount of heat absorbed by the system at constant volume. Right? Then case 3, for adiabatic process. In this case no heat change takes place. It means Q will be 0. If Q will be 0, then this del E will be is equal to minus W, or this work done will be is equal to minus del E. That is, it means decrease in free energy is exactly equal to work done on the system by the surrounding. This is the amount of work done will be is equal to decrease in internal energy as no heat is supplied to the system. Okay. For an isobaric process, this del P will be 0. In that case, this pressure volume work done will be positive. In case of del V is equal to 0, it will be 0, but in case of isobaric process, it will be positive, and this expression will be as such normal expression, that is del E will be is equal to Q minus P del V, right? Then come to another energy part, that is another type of energy, that is enthalpy. This enthalpy is denoted by H. Okay. This enthalpy is the total heat content of a system at constant pressure. When any process takes place at constant pressure, then it is the amount of heat, it is the total heat content of the system. Okay, and it is equivalent to the sum of internal energy and pressure volume work. Actually, this H, that is enthalpy, is the energy stored within the substance or the system that is available for conversion into heat. That is, amount of energy which can be converted into heat is called enthalpy. So it is called total heat content of the system, and H will be equivalent to E plus PV, that is internal energy plus pressure volume work. This enthalpy is also extensive property. It means it depends upon amount of matter present in the system, and it will be differ when you change the amount of matter, amount of substance present in the system, right? It is extensive property. Then it is a state function. It depends upon initial and final state only. That is, this del H will be is equal to H final minus H initial. It means this del H, that is change in enthalpy, will be is equal to enthalpy of final state minus enthalpy of initial state. For a reaction, this del H will be is equal to H product minus H reactant. Okay. This will be for a reaction. This enthalpy change for a reaction will be is equal to total enthalpy of product minus total enthalpy of reactant, right? As this H is equal to E plus PV. Okay. At constant pressure, this change in enthalpy will be is equal to del E plus P del V. At constant pressure, it will be equivalent to del E plus P del V. Okay. According to first law, this del E will be is equal to Q minus P del V, right? And at constant volume, this del E will be is equal to Q, right? If this del V will be 0, then del E will be is equal to Q. It is from first law expression. What is this? Change in internal energy will be equivalent to the amount of heat absorbed at constant volume, as work done will be 0 in that case. Okay. If you substitute this value of E, that is Q minus P del V, in this expression, then you will find this del H will be Q minus P del V. It is the value of del E, and then plus P del V, and then these terms will be cancelled, and this del H will be is equal to QP. What is QP? It is the heat change at constant pressure. Heat absorbed at constant pressure. Heat absorbed at constant volume will be always equal to the del E, that is change in internal energy. Heat absorbed at constant pressure, heat evolved at constant pressure will be is equal to del H, that is change in enthalpy, right? And you can write this expression, that is del H is equal to del E plus P del V. you can write this expression this way, that is QP. QP is equivalent to del H is equal to QV. QV is equivalent to del E plus P del V. Okay. QP is the amount of heat absorbed at constant pressure will be equivalent to amount of heat absorbed at constant volume plus P del V, that is pressure volume work, right? Then for gaseous reaction, this P del V will be is equal to del N RT. It is gas law. Okay. When del N will be change in number of moles in any reaction. Then you can write the expression for del H as del E plus del N RT. This type of equation can represent the enthalpy change in gaseous reaction. This del N will be summation of number of mole of product minus summation of number of mole of reactants. If this del N will be negative, then del H will be smaller than del E, and when this del N will be positive, this del H will be higher than this del E. Del H have the higher value than del E. It is the exothermic reaction case, and this is the case of endothermic reaction. Then you can write this expression for del H in this way, that is QP is equal to QV plus del N RT. These all expressions are important for numerical problem, right? Then come to condition for del H is equal to del E. In which condition this change in enthalpy will be exactly equal to the change in internal energy. What will be the condition? First condition will be del N will be 0. In that case, if del N will be 0, it means total number of mole of product will be is equal to total number of reactant in any reaction, then del H is equal to del E. Okay. Then for example, in this case, this hydrogen molecule, 1 mole hydrogen molecule, 1 mole chlorine molecule, and it will give 2 mole of HCl. There are total number of mole in product will be 2, and total number of mole in reactant will be 2, and change in number of mole will be 0. Okay. Second condition is del V will be 0. If del V will be 0, then this del H will be is equal to del E. If pressure volume work will be 0, then del H will be is equal to del E. It is the second condition. Then third, when reaction does not involve any gaseous reactant or product at all. If gaseous reactant or product are not present, then del H will be considered as equal to the del E. Okay. Because then pressure volume work will be absent. Then come to heat capacity. It is defined as the amount of heat required to raise the temperature of whole mass by 1 degree centigrade or 1 degree Celsius or 1 Kelvin. Right? If there is a system and it is the amount of heat Q supplied to the system, then temperature of system is raised by 1 degree and 1 Kelvin, then this amount of heat will be considered as heat capacity. It is denoted by C, and C will be is equal to Q by del T. Q is the amount of heat absorbed divided by change in temperature, right? Then another term is there, that is specific heat capacity and molar heat capacity. What is specific heat capacity? It is the amount of heat required to raise the temperature of 1 gram or unit mass of any substance. Okay. Then it is called specific heat of capacity, and C will be Q by m, it is the mass of the substance, del T, right? Then molar heat capacity, it is the heat capacity of the molar mass. It is defined as the amount of heat required to raise the temperature of 1 mole of the substance by 1 degree Celsius or 1 Kelvin, right? And for a small change, this C will be is equal to dq by dt, right? These two are intensive property, and but heat capacity is extensive property. It depends upon amount. If you change the amount of whole mass, whole system, then heat required to raise the temperature by 1 degree will be different. But specific heat capacity and molar heat capacity, these are intensive property, because here this amount of substance, amount of matter is specified. In this case it is unit mass, in this case it is 1 mole. Okay. In next lecture we'll start with heat capacity at constant volume, that is CV, and heat capacity at constant pressure, that is CP, the relation between CP and CV and all that. I hope you are enjoying the lecture, and thank you very much. Have a good day.